Okay, so we can start. I think that one of the highest moments in academic activity is when we can recognize that somebody who could have spent his life investing in more productive activities instead decided to dedicate his time, his intellectual resources, and is inventive to produce innovation, something which will not be used now and here, but probably in 100 years, and nobody knows where, maybe in Mars, if we colonize it. Just for telling you, Lagrange, the students, my students who are here, know that I have a kind of fixation about Lagrange. Lagrange studied many problems. One of them was to find a place in the solar system where you could locate a spaceship which would remain there with the same relative distance between itself and the other planets and the sun. When Lagrange formulated this problem, this was pure philosophy. And then it became a practical problem, and his solution has been exploited to send a telescope, which now is giving us an eye in the universe, giving us unbelievable information about what is happening there. Okay? So every society which had the intelligence to invest in people doing this kind of job, which is not remunerating now and here. Instead, it is remunerating for future generations and for every future society which will have a university, which will speak that language, which will be interested in those results. Okay, this is the difference between barbarians and Greeks. Okay? Even if your skin, I told you, is not white, you are Greek when you prove theorems Archimedean way. This is a cultural thing. We are inventing for the future. Now, it is my extreme pleasure, and I will give him immediately to talk, simply will tell you something about him. It is my extreme pleasure to be here honoring the choice made by Professor Auricchio to invest his life in producing solutions which will be used in the future centuries. His research is outstanding. He obtained wonderful results in computational mechanics. Then he dedicated to applications in mechanics and mathematics applied to medicine. Then he's the leader of a big lab working with 3D printing facilities. He will describe you what he's doing much better than me. There is also a personal relationship because we passed the same day the competition for becoming associate professors too many years ago, unfortunately. We are becoming old. Okay, so I think that this is very important for colleagues and for students, and this is one of the best moments of our academia, when somebody having competences not available in this university is coming here and telling us where we should go to understand something in that field. So I think I've spoken even too much, and I leave the scene to Ferdinando. Sì. Okay.
So thank you very much, Francesco, for the too long and nice introduction. In English?
In English.
In English, okay. I go with my presentation in English, and I'm very happy to be here and to talk about additive manufacturing, which is my the area on which I'm spending most of the time today. I would like to have this presentation possibly in a very interactive way, so if you have any question or anything that comes to your mind or that is not clear to you, please interrupt me and I would be happy to discuss with you. So additive manufacturing for me is really a new world full of opportunities and challenges. So it's really has completely changed my attitude toward research and toward applications. So it's really bringing many opportunities to me. So the presentation, I will start with a very quick introduction on additive manufacturing, on 3D printing. And then I will go more into, so I will also discuss a little bit what is the history of additive manufacturing in Pavia, in our labs. And then I will present several digressions on computational mechanics, simulations, and other directions on which we are currently working in order to show that there are many opportunities. And then I will close up with my presentation. But I really look forward for interactions, idea exchange, start new research activities, joint research activities, and so on. So what is additive manufacturing? Additive manufacturing is known also as 3D printing. I guess almost everyone in the room already heard about 3D printing. So it's a manufacturing technology. So it's a technology where you want to produce objects. But it's a very clean technology. And it's a technology which is different from traditional technologies because in general the most classical traditional technology to produce objects is a subtractive technology like machining, milling. So you start from a big block of a material and you remove the material that you don't need. That's the traditional way you produce components. Instead, with additive manufacturing, you produce the object layering down material layer after layer, depositing layer after layer all the material that you needed. The very interesting thing is that you always start with additive manufacturing from a virtual model. So you draw your object of desire with the computer, then you slice the object, so you virtually divide your object in slice, and then you progressively, you have a machine which deposits one layer after the layer. So here you can see a pictorial reproduction of the deposition process. So everyone knows about the 3D printing, I think, and one of the reasons is that this technology has some features which you don't find in standard technology. Additive manufacturing is a native digital technology, is a very democratic technology, and it's a very material-dependent technology. When I say it's native digital technology, I mean that's really a technology. I mean, this process was born originally in a native in a digital environment. So really 3D printing is a digital technology. All the traditional technology have been transformed to become digital, but I think that additive manufacturing in a sense is more digital than the other technology. The other reason why it's well known is because it's a very democratic technology. What does it mean? It means that you can find 3D printing machines which are very cheap, like 200 euros, 300 euros, up to very, very expensive machines, 2 millions, 3 millions of euros. So depending on the budget you have, you can buy your own machine. So it's a very democratic technology. So you can find these machines, in many houses, in the basement, in the garage with kids playing with these machines, but you find these machines, very advanced machines, in the top level labs in the world. And then the other thing which is really bringing up my interest is that it's a technology which is very material dependent. So under the umbrella of 3D printing, in reality, there are many different technologies, which I will discuss shortly. So you can wonder how old is this technology, because nowadays it's becoming to the attention of many people. Everyone knows about the technology, but it's not a very new technology. So since the beginning of the century, basically, The Economist already published, was somehow advertising the technology. Forecasting was coming a very technology with a very high impact. So you can see this in the 2011. It was already saying that you could eventually print your own Stradivari violin with this technology. But in reality, it's a quite old technology because the first system, goes back to the 80s of the previous century, where you had, the first machines which somehow could have been 3D printing. But being Italian, what was really impressive is that, so on the left side of the slide, it's really technology. On the right-hand side instead, but it's really surprising, so I'm very happy to bring it up, is that even in some of the novels from Primo Levi in the 60s, you could find a vision of exactly this technology. So Primo Levi wrote a novel regarding Mimete. Mimete was a machine, so it was just in his imagination. But in 60, he imagined a machine able of duplicating an object identical to the original one. So there was this inventor who invented these machines, and then he wanted to try the machine. So the first thing he did was to insert in the machine a paper sheet with a stamp. And on the other side of the machine, there was a copy of the paper with the stamp, which came out identical. So it was really a machine able to reproduce really valuable object. But then he tried to increase the expectation with his machine. So for example, he started to use, he tested the machine with money, with the banknote, and then with a diamond. And then the machine was able to reproduce the object. And then he tried with a salamander even, so, a live animal. And the machine was able to reproduce the object. And then he even tried to duplicate his wife. But then the novel finished with the fact that, after a while he was getting too tired of having just two wives, so he even duplicated himself in order to form two identical couple. And it's incredible because it's just imagination, but if you see the way, if you read the novel, it's exactly the way the machine is working these days. So, but I told you that the technology is not very new, it's very wide, and in fact, I would like to spend a little bit of time describing the technology. So I told you that you start from a drawing, you slice the object, and then you 3D print it, layer after layer. But in reality, there are many different technologies. Probably I'm saying things that most of you already know. But the technology goes from the standard material extrusion, the FDM technology, where you deposit, a thermoplastic material, a layer after layer, a wire after wire, or you can start from a bath of material, from a bath of resin, a liquid bath, and with the laser, you cure your material, you transform your material into a solid, and you extract from this very thin bath your object. Or you can have material jetting, so there is a head which is moving, and the head is spraying the material, is spraying a liquid material. At the same time, there is a UV lamp which cures the material. So I'm showing you the technology increasing in terms of investment cost that you need to pay to get the machines. Or, for example, there is a direct energy deposition technology where you have a head, you have a laser, you have two regions where you spray powder, and the laser melts the powder, and if the system is complex, you can really build very complex objects like this. You see, very, very, very funny geometries. Or finally, which is probably the industrially most valuable technology in this day, there is powder bed fusion. So you deposit a layer of powder, and then with the laser you melt your material, and then you move all the component down, and you deposit another layer, and then you keep lasering and melting the material. So you can see you can obtain very complex geometry. Ideally, it's a free-form production technology, many different materials. With this technology, you can 3D print polymers, metal, ceramics, many different things. So it's a very broad technology. So going back to why I started to be interested in 3D printing, everything goes back in 2010 when we had a master thesis in bioengineers, and there was this student, Stefania Marconi, which developed a tool, a software, to find a tumor in pancreas, pancreatic tumors. And then, so he developed the algorithm to highlight the tumor. But then, besides showing nice pictures on the computer, the idea was that came to the surgeons with whom we were working. He asked us if we were able to reproduce the object and, you know, to go to the discussion with the object. And at that time, we started to learn about 3D printing, and I got immediately really involved in the technology. I really felt in love with the technology. I didn't know, you know, really what was the final use I was going to do with this technology, but I decided to buy the one machine. And since then, there has been many, many steps. But everything started from a medical request. So the activities of use of 3D printing in surgery and giving medical support is really very, very important activity for our group. In fact, nowadays, we have a lab within the new building in the hospital, in the San Matteo Policlinico in Pavia. So we have a lab which is situated in a very critical area because it's the place where all the patients get accepted in the hospital. So everyone can see the lab, and everyone can see, even we have a wall where we have a description of our idea of the use of 3D printing in surgery, and we have a bunch of different examples of 3D printed components. And we opened this lab in 2017, and since then we've been interacting with many different specialties. So all these are some of the specialties with which we interact. And you can see here different reproduction of human parts, of human components, okay? And the very interesting thing is that behind every single part, you see these objects which have a very funny shape with colors, maybe soft, but behind every one of these, there is a name, there is a patient. We always start from CT images, DICOM images, and so these are a reproduction of a human component. And using this reproduction, we give this reproduction to the surgeons, and they do many different activities. So one of the first applications is for morphological aspects. So they use these components that we print also with different colors in order to highlight tumors, vessels, arteries, veins, and so on. So they use it a lot to plan the surgery. They use it a lot also to talk with patients. They find extremely useful to talk with patients. So the first use is really as a map, basically as a map, in order to understand how to approach the surgery. Clearly, we are also very much interested into the mechanical performance of the material. So here you can see, for example, a very simple test where we punch a specimen of a 3D printed material. So we do the punching of human tissue and the punching of the 3D printed tissue, and we try to compare the performance, because the idea is to reproduce the mechanical features of the human tissue. And for example, this is a very interesting area of research, because it's completely, the ability or the mechanical property of the tissue in order to be suited is something that's completely unknown. Surgeons have an incredible ability to sew tissues, but no one gives information on the quality, on the mechanical properties of the material. So we do mechanical testing in order to reproduce the mechanical feature of these components, and nowadays we are able to reproduce even complete district of the human people. You can see here the abdominal part. This is planned for living donor kidney transplantation, and we reproduce with medical images really the complete abdominal part with the right mechanical properties, and basically we give these components, you can see the component down here, to surgeons, and they test the procedure in a very valuable and realistic surgical environment. And nowadays, we not only reproduce tissues with the right mechanical features, with the ability to suture the material, but we are also working on the fluidic part. Now you can see a lot of leakage, but basically we are reproducing with 3D printing the organs, and we use pulsatile pumps in order to give the pulsatile effect to the organs, and in order to make the behavior of the tissue even more reliable and realistic. And we are also working a lot on the echogeneity of the material in order to get exactly the same behavior of human tissue, for example, under echography. So in order to make it not only geometrical, the specimens equal to the human being, but as much as possible equal to the human being. So everything started from medical requests, and again, today we have a lab, an active lab in the hospital. We just hired we had 2 permanent positions in the hospital, and now we have basically 2 engineers which work full day in the hospital supporting all the activity. But another moment in which really changed my life was in 2015, when 3D printing was chosen as thematic subject for the whole university. And I was proposing this project to the university, so the project got the best evaluation among all the projects. So since 2015, 3D printing has been a thematic subject for the University of Pavia, and since that time I really had to put all my efforts in these directions, because I got the rector gave me some funding, so I had to really prove that there was a good idea to choose 3D printing. So we started with this strategic project. We had the different pillars. You can see that there was a pillar, so modeling and simulation. Professor Dell'Isola was telling I do computational mechanics, which is absolutely true. So there was a pillar on simulation, finite elements, modeling, but there was a pillar on materials, because I've always been very fascinated by materials. There was a pillar on manufacturing, and this is one of the areas in which we put most of our efforts, start labs. Then there was a pillar on applications, because I throw all the applications in one basket. I didn't want to focus only on medical application, but all sorts of applications. And then a pillar on social economical impact. But one of the major pillars, especially for us, was a kind of a new activity, was to start labs. Labs where we had technology. So now we have the lab in the medical school. We have another lab, we have more than one lab in engineering, we have another lab in the chemistry department, so we have many different labs. This is the lab, this is a picture of the lab, which we have in the engineering school. If you come and visit me, you will see this lab, which is named Proto Lab. And in the years, we have put a lot of efforts in order to get many different machines, very cheap machines or more expensive machines. And the very interesting thing is that nowadays, we have many machines. We don't have all the machines, so I always want to buy more machines. But what is very interesting, if you see these diagrams which reproduce density versus Young modulus, so it's a very simple way of categorize materials. With our technologies, you can really go from a very highly performing stiff materials like metal, composites, ceramics, to very soft materials like polymers and rubbers, okay? So we really cover a huge spectrum, not only on machines, but a huge spectrum of different materials. So we can 3D printed metals, we can 3D printed composite with fibers, long fibers, so very stiff. We can print polymers up to soft polymers, soft rubbers, okay? And with all these machines, we do a lot of 3D printing of different objects. You can see here very complex geometry. Each of these pictures has a project behind it. So in the previous picture I was showing you there was a name. Here, usually behind every single component there is a name of a company or a colleague for which we do 3D printing. So you can see here a lot of steel components, very complex geometry, a lot of plastic components. These are made of nylon with very fancy geometry. And going along with these activities, we also realized that it's not only necessary to 3D print a component, but unfortunately, when you start to talk with company, you need also to polish and finish your components. So at the end of the story, we bought also a milling machine, a 5-axis milling machine. And so what we do, we start from a cut, we 3D printed the objects that we want. We 3D printed also the supports to do the machining. We do the machining, so we refine the component with a subtractive technology, and we come up with the final object. So with this technology in our labs, we do a lot of interactions with companies, and so I'm showing you some of the most recent activities, but we really have many things running. So here there is a collaboration with ABB from Dalmine, and basically they gave us a challenge. And the challenge was to reproduce, to redesign this component. So this is an assembly which is rotating, is a shaft that's rotating around these 2 points. And basically it's a switch of an industrial, it's an industrial switch, okay? So it's like a switch like this. Unfortunately, the component has this dimension. And that's the way they produce it. They produce it with a tube, with a metallic tube, with a bunch of different components. They had basically 20 steel parts, and it took them more than a month to get the component when they needed in order to obtain and assemble all the components. And we redesigned the object. You can see the same object, which is rotating around the same 2 points, but now it's produced only in one component, and you can produce it only in 4 days. So a drastic reduction of time, of lead time, and the cost is basically the same. So the way we did it, we obtained this funny geometry is the following. So we started from the original constraints, from the original domain, and then we define a volume where you ideally could distribute your material. So we highlight the exclusion regions, which are the constraint, the design constraints, and then we start to run optimization. Optimization is a numerical tool. Well, I don't know why it's not running. Okay, here you can see it's an automatic procedure where you reduce progressively the material, and then once we obtain the final component here, then we slice it and we send it to the 3D printing machines. Okay, that's the 3D printing process. And then the very nice thing is that once you produce your component, you can also go to your lab, to your mechanical lab, and you can test it. You can see here the component coming out from the machine. We do a little bit of sandblasting, and then we put it under mechanical machines. We construct also all the supports to do the mechanical test, which is really interesting with additive manufacturing. And then we did the force displacement test in order to measure the performance of the component. But again, there are many collaborations. I'll show you one, the first collaboration. Here is a very recent collaboration with a very small company from Lago di Garda, it's T-Red. They basically produce high-level bicycles for racing, indoor racings, and we are supporting them in the design optimization of bicycle components. You can see here one component on which we're doing mechanical analysis. We are also 3D printing makeup of the bicycle. So this is a bicycle which you cannot ride, but for example, you can put it in a wing tunnel in order to do experimental tests. So these are really prototype. And the very interesting thing is now that this company is bringing its athletes to the world champion and to the Olympiads, and you can see that they are running with our logo. So you can see our logo, Protolab here, and our CompMech logo here. So we can even say that we're sponsoring an Olympic team, cycling team here. And with this company, we're doing a lot of optimization and 3D printing. And here, for example, you can see the 3D printing of another component, the bicycle. And you know, the standard geometry has more than half of a kilo of weight. And with the design optimization, we basically recover more than 25% of the weight with the same stiffness. So you can really make components with the same stiffness and much lighter, so you can get a huge benefit for the athlete that's competing. But there are, you know, this is for fun more than anything else, but there are also other applications, like for example, this is a very interesting collaboration with La Marzocco. La Marzocco is a coffee maker, producer in Firenze, and with them, they basically had the request of increasing the temperature of the component where they produce the coffee, and we did some numerical simulation, some optimization, and the very nice thing is that we could 3D print the object, we could bring the object to the machines and make some coffee and really test it and see if we were getting really a benefit with our
I will be interactive.
Huh?
I will be interactive now.
Please.
You are Neapolitan. Your problem is producing better coffee, right?
Exactly, but to produce better coffee, they want to increase the temperature because now I don't remember probably traditionally the temperature is, I think it was above 70 degrees Celsius, but then they changed, in order to make it a more clean production, they changed the material to steel. And steel has a better conductivity, so they were not able to reach the same temperature. So they lowered the temperature for the machines from 75 to 65. And so we had to increase it again. And so it was a very practical, and being Napoleon, it was a very important point. But it's very interesting that you can do simulations, so computational mechanics, then you print the object, you see the object, you bring it to the company, you do the testing. So it's beautiful. And now we are also opening other activities. For example, this is another very interesting application. This is with Memetis, with the German company which produce fluidic devices. Basically, they have one inlet and 4 outlets, and they have 4 valves. So they control you know, the amount of fluid which is distributed in these 4 points, and they want this object to produce with peak, because the fluid they delivery is a very aggressive fluid. And we were optimizing the object with 3D printing, doing the simulations, producing the object and shipping the object to the company. But you can do many different things. For example, here is a very nice application, because you can see also for cultural heritage. You know, your reproduction of this is a small scale, but you can reproduce statue, you can reproduce vehicles from pictures, from drawing. This is a very interesting example, because they were only the drawing, and historical researcher on cultural heritage were not able to understand if the machine was really able to work or not. So we produced a fully working machines, and they use it, you know, to derive conclusions. And the incredible thing is that in this application, you not only reproduce the geometry, but also here you can really reproduce the texture of the material. So when people see this object, they say, "Oh, it's made of wood." No, it's made of plastic with a superficial texture which resemble wood. Or here it's marble. No, it's plastic again. But you can take picture of your component, or you know, the shadow of your statue, you can 3D print the object also with the right pictures on the top. So it's a really active and creative field. So I hope that with this first part of my presentation, it was clear that really 3D printing, it's opening you a lot of interactions, a lot of ideas, a lot of new concepts. And in fact, you know, with the labs that we build, I mean, these labs are not only university labs, but they're really production sites. It's a really place where company comes, they see prototypes, we discuss about them. So it's a very interesting directions, because you really shorten a lot the line between design, production, and application of your components. So it's really a fascinating world. But then it's also a fascinating world because it's opening you the door to many more theoretical applications or numerical applications. Now, I don't want to go too much into details, but I was showing you that one of the things that you often do when you start to talk about 3D printing is optimization. So basically, if you look at this object, this is a cantilever beam, okay? So it's clamped here, you have a load here, and now the question is, where do you want to put your material in order to have an optimal performance of your structure? So you can decide that you put your material uniformly inside your domain. So your design domain maybe is this rectangle. You can say, okay, I want to put my material uniformly in that region. Or you can distribute the material in this other way, where there are white region where you don't have the material and red region where you have the material. In order to do this optimal distribution of material, you need to have theoretical framework and numerical tools to do this. And this goes under the name of optimization. And the incredible thing of optimization when you do 3D printing is that you have a lot of freedom where you want to put material, not only, but you can also, for example, you can also decide, you know, the internal structure of your material. So it's not only where you put material or you don't put material, but for example, let me go directly to the examples without going to the mathematical. Well, I mean, you can do a lot of theories, a lot of integrals, minimization, phase field theory. You can develop your numerical tools, staggered, monolithic. So you can do a lot of theoretical research. But at the end of the story, you can solve problems like this. This is a three-point bending problem. So you have your beam. Your initial domain is a rectangle. It's simply supported with the central load here. And you want to know where you want to distribute the material, and also not only where you want the material, where you don't want the material, but eventually you want to say also in certain region I want to have a more dense material, in other region I want a less dense material. And the final solution is this one. So the black and white means no material, black means material. And the colors, the red mean more dense material, which is on the supports, where you have the load, and here, and the green means not dense material. And once you have this numerical tool, you run it, you get the numerics. The very nice thing is that you can do the test. So here on the left, you can see a beam, which is exactly a reproduction of your numerical results. So you have more materials on the supports, more materials here, and less material here and here. And here you have the standard beam. So it's a rectangle with a uniform distribution of material. And if you do the mechanical testing, this is a standard mechanical test. So it's a force displacement response. You can see that the standard beam is this one, and the optimized beam behaves like this one, with the same amount of material. So it costs the same. But in this case, you distributed your material in a much better way. So your structure is much more stiff, so you're using better your material. So this structure is more optimal in this sense. And you can do a lot of other things. Again, you do a lot of theory, theoretical frames, again, with integrals. You do a lot of numerics, with convergence. You know, you study, you vary your parameters and see how your algorithms are working. But then of the story, you can do numerical simulation of applied problems, and here you can see, for example, a bridge, where again you distribute optimally your material. I don't want to go too much into these details, and we leave it, for later discussion if you are interested. But again, I talked about topology optimizations, but there are many other concepts, that came to my mind while working in this area. For example, another area of high interest is to simulate the process, and this again came from a clear request. You can see here a real problem that this is a plate. This is a square plate where we 3D printed a lot of components in our lab. And this plate, we were not able to finish the production of these components. And the reason is very clear, because basically you can take the plate, you can put on a table, and it can rotate very easily. What does it mean? It means that the plate, the spine it was like a 2 centimeter steel plate. It completely bended, and it broke the screw that was tightening the plate to the machines, because there were too much residual strains in this component. So it's really important to model, again, to do the models and the numerics of the process. And you can simulate the melt pool analysis, so the laser which is moving and melting the material, or you can reproduce the complete object, okay? And again, there are many different approaches. Here I'm really going very fast, because with these very complex problems, there are new numerical technologies that you can use. Here I'm talking about the finite cell methods. This is let's say, a non-conforming numerical methods. So if you want to study this object has a complex geometry, and you study this object not with the standard finite element methods where you describe your object with your mesh, but you immerse your object inside a larger mesh. So the mesh in this methodology has a very uniform, very well-defined mesh, very regular mesh. And you describe your geometry locally, increasing the number of Gauss points. So you increase the number of integration points locally, and with this trick, you can basically obtain a very well-performing numerical method. With this technology, we are able to simulate, components like this. These are strut-like components, grid-like components, and when you do these grid-like components, you want to make it really small, which is not very engineering-oriented, but people want to make very small. So you start to have huge defects in the production, and you need to capture these defects, otherwise you don't reproduce the behavior of your component. So we did the numerics, we did the 3D printing of the objects, we did CD scans of the object, and we did the mechanical test. And let me go just to one example. Here you can see for one set of experiment, you can see 3 columns. So the yellow, the orange column is the numerical as designed. It means that we took the CAD and we did the simulation. So we simulate the 3D point bending of this beam starting from your CAD, so from the ideal geometry. So we draw the geometry, we did the simulation, and that's the value of the displacement that we were expecting. Then we did the 3D printing and we did the experiments. And you can see that there is a huge difference between the predicted and the experiments. Why? Because the real geometry is very different from the produced geometry. So what we did a CT scan of the real object. We mesh with the technology I was showing you the object. We perform again the numerical simulation, and we get the green response. So if you really take into account the geometry, you really could get a good prediction. But you need to take into account the real geometry. And it's quite easy to do this if you have these immersed numerical techniques. From this area of research, I get really interested in these immersed technologies. So we start to develop other technologies. And the challenging aspect is that with this 3D printing, is that basically you wanna construct a complex object. And the way you construct it is layer by layer. So at a certain point, your domain is up to here. So you have a yellow part, which is going to be built, and you have a gray part, which is really already built. But so you have an evolving domain. So it's not like you start from an object from the beginning. It's a growing domain. But it's not only this the issue that you need to modify your computational domain at every step, but the very complex aspect is that you have a very local, highly nonlinear phenomena in the top area, because you have the laser which melt the material, so there you have a very complex nonlinear behavior, and then the response of this layer really depends on the remaining part of the body. So it's like you want to do the simulation in this area. In this area you need to be very accurate, but at the same time you cannot neglect the remaining part of the body. Consider that the component I'm showing you are, the standard dimension of the object is like 10, 20, 30 centimeter, and this layer is around like 200 microns. So you want to have like a mesh which captures nonlinear phenomena in 200 microns layers, but at the same time you want to capture the whole thing. So we come up with some new numerical techniques where you start with a large mesh, you activate only part of the mesh, and then locally you have, even on the top of the crude mesh, you have locally a much finer mesh. And you can do these things with the so-called two-level method, which is a method which is very well known in the numerical analysis community, in the math community. Here there are some concepts, another name which comes to the very easily in the literature is the so-called fat boundary method. But the very nice thing is that basically, if you have a domain with an inclusion and you have two materials, you can rewrite this problem as a problem in a large domain, and so a global problem and a local problem. And if you iterate between these two problems, you go back to the original problem. So there is a lot of math theory in this aspect, but the very nice thing is that you can develop all your theory, you can do this multi-step also not only in space but also in time, and with these tools basically we develop some numerical tools where basically we're able to predict locally the melting pool, and this seems to work in a very nice feature.
So you are trying to optimize the 3D printing process?
Yes, exactly. Yes.
Are they following your indications?
They are not following my indications because there are other colleagues which have more impact. They are interacting with with companies that produce the softwares. But this is a very advanced area of research. So the research is having an impact in the design. Yeah, sure. Or, for example, you can do other considerations where basically when you produce your object, you design where you deposit your material. And then you could ask yourself, okay, if I need to deposit the material in a certain region, what is the optimal way to deposit the material? Usually when I talk with mathematicians about this problem, I always say, if you need to paint a facade or a wall, okay, you have the surface, like the wall that's there. You have the surface, the surface, but what is the optimal way to cover that surface, completely? So again, it's an optimal problem. What is the best way of painting? And here is exactly the same concept. You have a volume that you want to fill it up. What is the best way to deposit your material? Considering also that if you deposit in different ways, the mechanical performance could be different. So let me come directly to the final to the examples. You can see here 3 mechanical examples, very simple. You have a specimen under uniaxial traction, so it's clamped here, is there is a uniform force, horizontal force here, and there is a hole. We know clearly what is the best way of putting the material. The best way to put the material is to go around the hole. But this is the theory. Then we are able to show it numerically, and we're also able to 3D print the component. Here you can see a component with a lot of space between deposition of material, and you can see that the material goes around the hole. And you can see the same specimen where now the material is very close to each other. Or for example, this again is a simply supported beam with a uniform load, and here it's a little bit more difficult to understand what is the optimal distribution of the material, but if you study the force lines, you know how you should put the material. And here you can see again that we can optimize the material distribution, and we can produce a specimen with only a little bit of material, or we can produce with a lot of materials. Or here there is again a specimen with 5 holes. So the very nice thing is that, again, models, theory, numerics, applications. You produce the component, you go to the lab, you test it. You see what you know from your theory. So it's really, really interesting. But again, 3D printing is opening a lot of different activities in our group. So here, I'm just mentioning few activities. These are very nice research that we are conducting. Basically, we are doing, these are new 3D printing technologies. The concept is to 3D print an object in a cheap way, so develop technology which produce object in a cheap way, and then go through the binding and sintering process in order to get to the final object. So conceptually, this object I'm 3D printing here, depositing this paste, is made of plastic, or like a material which is very cheap, but it's filled, for example, with a lot of power of metal or ceramics. And then we bring the components to the oven, and we do the binding of the initial material, and then we do the sintering of the material. So we end up with the components which are either metal components or ceramic components. And this is where also industries are going a lot, because this way of reproducing has a lot of benefits, in particular in terms of cost. Or, there are other technologies on which we are working, which again are based on sintering, so produce an object and then do the sintering of the component. But there are many other activities which are really bringing our attention in these days. There is the 3D printing of concrete structures. You can see here robots that we have in Napoli at Federico II, with which we print walls, we print beams with very funny geometry. We do a lot of bioprinting. This is a very fascinating technology. So we print hydrogels with cells, and we get differentiation of the cells in order to, so this becomes constructs where the cell can grow in the fair shades, or you can produce objects which feels like the environment, and they can do very complex movements. So here you can see, okay, here you can see like a component which is opening first on one side and then on the other side, or this component which is, let me run it again, it's starting from this geometry, and then first you close this part and then you close this part. So it's a very complex movement. You can get it. So these are the so-called 4D printing components, because they're not only 3D printed, so you can get very complex geometry, but you can involve also time, because you change the environmental condition, the component feels the change in the environmental temperature, and you can produce very complex objects. So we do a lot of activities in these directions, which again, let me stress it, that it opens the door to theory, numerics, and a lot of applications. So it's a lot of fun. But clearly, let me come to the final closure, and really the final closure, can only go with a special thanks to all the people which belongs to my groups, And a special thank goes to Massimo Caraturo, Stefania Marconi, Gianluca Laimo, Alessandro Reali, Michele Conti, and Simone Morganti, which are really, the main driving force around these activities. But I would say that the whole group of people is really active in 3D printing. So I hope that I show you that 3D printing or additive manufacturing is a real breakthrough technology, and I'm sure that in the future you will hear more and more about this technology. Thank you. I know I had you say 4 hours of talking, but
4 hours of questions.
Yeah.
Questions? Please.
Yeah, thank you so much. I have 3 questions. Sorry, my first question is, how do you... Yeah, thank you, Prof. I have 3 questions, and my first question is, if you want to do 3D printing, how do you capture the what's called exact image? E.g., if I want to do the 3D printing of this phone.
No, say it again.
If you want to do 3D printing, how do you capture the exact object you want to print?
There is always every time you produce something, you create something, there is always an error. So ideally, it's also the picture, this is drastic, and I can give you an explanation why, but the concept is the same. So ideally, here, we had a very clear geometry that we want to produce it, but then the geometry wasn't so precise. So there is always a limitation in the production technology. So the standard production technologies in these days, it's around, let's say, 200 microns. That's the best, 200, 300 microns. These are the best you can get it with standard industrially valuable components. And if you try to go smaller, you start to have defects. So if you want to produce an object which is like few centimeters, and this is the tolerance, you can do a very good job. If you want to produce an object which has very complex geometry, with details which are very small, you make a mistake. The only way you can control this is knowing the technology and try to control it. In reality, there are some, let me go back to another slide, which was very fast. You can try to help a little bit with simulations, but it's not really, you don't go too far away. You can see here an object. This was the object as designed. We 3D printed, and that was the object 3D printed. You could see that they had a huge defect here. So you can do the simulation of the production process, so you can compute this error, and you can correct the initial geometry in order to control your error. But you cannot go, below certain tolerance. So there is always an error. So you need also experience plays a lot of role. That's one of the reasons because I really push into the lab. We really want to have the technologies, we want to have the machines, we have a collaboration with companies because we need to run the machines. I always say the machine should run the whole day long, which is not the case, but they work a lot because the more you do the 3D printing, the more you learn.
Yeah, thank you so much, sir. Yeah, you talked something about defect. That's what leads to my second question. Let's assume that probably you do a 3D printing of an object. You have already produced it, and probably you now find out that it has a defect. How do you correct it? How do you correct it? Is it that you're going to destroy the whole of the object and create another? You said 3D printing works layer by layer. Is it that, how do you correct if you detect a kind of defect in a particular object that you produce, that you do the 3D printing? I don't know if you get my question.
No, not completely. Rephrase it, please.
Yeah. What I mean is that if you have already produced an object or something using 3D printing,
okay,
you know, it works layer by layer.
Sure.
And if you now find out, probably when you are doing the experiment in the lab, you are trying to do the simulation, you want to see how effective or how, what's it called, how efficient the object is, and you detect a defect. How do you correct it? Is it that you would...
I see your point. This is a very good question. This is one of the industrial challenge that you have it today. So first time, first right. So, so the way companies do it now is that they scan, they have cameras which scan the process. So every time you deposit a layer and the laser goes, there is a camera which takes pictures, and you control if you have an anomaly in your process. The question is, okay, that's expensive, but it's the easy way. But the point is, what do you do when you see a defect? For example, you know, powder. The powder, when we talk about the metal printing, you know, you start from the metal powder. So I was showing you. Let me go back. Okay, to this technology. So you deposit a layer of powder, and then you fuse it. And then you deposit another layer of powder. Now, this powder is highly controlled, but I mean, there is always, you know, an envelope. There is, I mean, it's not like just one material. So you have a material distribution. So possibly you could have a mistake during the production. You can have a defect, or even, you know, the example I was showing you. Let me go back. This one. This is a very simple geometry. So when they ask us to produce it, we say, oh, that's simple. And then we come up with a defect, a huge defect. So the question is, what happens when you are producing the component? So here what we did was, we produced the component, we observe a defect, we rebuild the component, correcting the geometry. But your question, if I understood correctly, is what happens when you are in the process and you see a defect, what you can do? This is very complex. So what people do, they take pictures, they take movies of the productions, but it's not very clear what you can do when you see the defects. So, because I mean, you need to have a very quick simulation tool which tells you if that defect is defect that you can correct or not. So, for example, you could go again with your laser, then fuse again the material, but are you going to get it the same mechanical performance or not? These components are expensive. So it's a very open question, and the idea is to go with you know, standard tools of machine learning, simulations, you know, combining many different technologies in order to control the production process. But it's not easy, because this process is a very local process. So it's highly nonlinear, very localized. So you can have huge issues here. For example, I could ask, why did we get this defect? Do you know why? It's very simple. Because you see that we had supports. So while we were producing, so if we were at this level, so we could produce a component in this direction. So when we are here, we only produce this piece. When we're here, we have three different pieces. When we are here, we at a certain point, we completely change the geometry. So we go from three components, because if you draw a line here, and you saw what's below, it's three parts. When you see what's above, is a unique component. So the thermal field is completely different. So this line, I mean, it's very simple to understand it now, but this piece had as a defect because there was an abrupt change of thermal response of the component when we start to produce this line. And you know, the amount of heat that we were sending to the plate was not enough. So you can, correct your design. But what happens when you're in line, online, and you start producing? Like, again, I show you this example. Where it was. This is a very personal example. Again, we got it into the lab. Again, this is I think it's a 2 centimeter slab, and we put a lot of components. So to produce this component was probably like, I don't know, 2,000 euro. So we throw 2,000 euro, which is not, ideal. And not only, but we could have even broken the machines because, the plate was bent. So it was really a problem. Now we have plates which are like 4 centimeters thickness, huge. And you need to take care of these things. So that's another challenging but fascinating area.
Yeah,
so there is no solution today.
Yeah, thank you so much, sir.
You're welcome.
Okay, I have.
Can we use, for example, smart alloy, which made from different materials? Smart alloy.
Like which one?
Nickel, magnesium,
Magnesium is very easy. Nickel also, it's a more advanced topic, but there are labs like the CNR in Lectio which does it, or there are other companies which produce it. Yes, again, if you know these materials, you need to really control the production process. So it is, in general, it's difficult to produce it with the standard technology. So with this technology, it's even more difficult, but people can do it. So people do it today.
Okay, thank you.
The issue, I always tell to company that there is a factor of 10 in terms of cost. So if you produce a component of steel, you can produce the same component with this technology, but it costs 10 times the same amount. So you need to get the benefit in terms of geometry, material that you don't use, whatever, performance, that must cover this gap of 10 times the cost. So consider it with respect to smart materials. They're already expensive.
For example, if we are using same body, can we change the material from
Point to point?
Yeah.
Yes, absolutely yes. If you are able to do it, yes. This one direction. You do everything with the laser. So if you have your own machine and you can control the laser and you are able to do it, you can fuse the material in a different way in each single point. So you can do it. Not easy. People don't do it too much because it's very complex. But yes, so you can design your component in order to produce your component with different material properties in each single point. Absolutely yes. So conceptually you can do it. You don't see much of these things around, but ideally yes. Probably in a few years it will come out.
Anyway, in France they claim they can do it, but it didn't work up to now. French are, I would not tell the name of the group.
You need to, there is a lot of efforts, but trust me, there is a lot of efforts in running these labs. It gives you a lot of energy because you see the components, you play with the components, you learn a lot from the components, but you need to put a lot of energy. It's not easy to run these things. So the technology, on one end is very easy, on the other end is not so easy. But depends the way you see it, because we are a production lab now. We used to only to do numerics. Now we produce components. We are like a factory.
This is for proving that mathematics is very important in engineering.
Absolutely.
Because now you design things with optimal algorithms, and then you get the object itself. It's a question of transforming dreams into reality. Other questions?
So what about post-processing of specimens? Because there are some specimens that have been shown that for sure wouldn't keep their shape at those high temperatures. And so how do you get them to recover the shape that you were designed?
This is part of the design process. This is a huge problem. Again, the production process, let me say it again. It's a layer by layer, very localized, highly nonlinear locally, so at the end of the story you can really accumulate in your specimen a lot of residual strains. And these produce internal stresses. So you can take the whole plate once you have produced it, and depending on the material, you can put in oven and release all the stress. Clearly you change the structure of the material, so it's always a game, and you need to design the thing. But standard procedure makes you general, so you do the production, especially with the metal, you do the production, and then you do the stress release.
Is the role of gravity important?
No, not to my knowledge. No.
Sorry, I said I have 3 questions. This is my last question. What are the current limitations of the technology, and what are the possible research areas?
What are the limitations and?
Yes. The limitation and the possible research area.
Possible extensions.
Yes, the extensions.
So the limitations are of the machines you buy today are the precision, because if you compare with mechanical tooling, this production technology has not the same precision. You know, with tooling you go to like 10 microns, 5 microns, it's really small. With standard technology, I told you, it's like 100, 200 microns, so you don't get a very smooth surface. It's also today technology is the powder, because the standard powder is around 40 microns, the dimension of the powder. But you know, this is the standard powder, but conceptually you can go to any powder. So the future is that you can really extend this technology with a much more precise laser, with much smaller particles. So there are machines, for example, that are based on the femtosecond laser, which are very small, much more precise lasers, but these are very expensive machines. For example, we don't have it. So there are limitations, so it depends on the technology. So again, 3D printing is a very broad family of technology. So we should say, I should ask you, to which technology are you referring to? To which powder are you referring to? To which, you know, metallurgistic process are you referring to? So it really depends. But this is also a world of opportunities, because you can design, you know, different materials, you can get different processes. So conceptually, there is no limitations. You can go very, very small, very, very big, and then, sorry, there are limitations, because, you know, it's not, I mean, nothing is for free. But so it really depends.
Okay. You are not sleeping.
Yeah, thank you so much for the presentation. I was just wondering, how do you convince your university to engage in such a huge project? Like the project formulation, if you can take us through.
How did I convince my university to
Yeah.
go through the process?
Yeah.
I didn't convince the university. Since it was an idea of my rector, of the previous rector, Fabio Rugge. He used about 20% of the university budget to open this idea of strategic teams. So he just opened a competition. So everyone could have applied for this funding, and each single project got about 1.8 punti organico, which means a lot of money in terms, because these are positions, it's a permanent position. So it's like, you know, 2 full-time professors, or, you know, many research and so on.
I think something like 2 million euros.
I don't know in terms of money, but it's a lot of valuable money in some sense, because these are positions. And he came with the idea of opening to new projects, and he was looking for multidisciplinary, transversal, broad projects. So there were many, I don't know, like 25 projects that were applied, and only 5 were chosen in different areas. there was one on, for example, on law and communication, like to make law rules, being able to how to write laws in order to make them simple and effective. So it was in all areas, but there was an international committee from all over the world of, I don't remember, 5, 6 big professors. They came to Pavia, they interviewed all the proponents, and then there was a voting rate and so on. And I should say I'm very proud because we were evaluated as the first. I was lucky because, 2015 3D printing was starting, so it was...
Neapolitans, for being appreciated, must go away from Napoli, right? So it seems a tragedy.
So it was not me, it was more like I was at the right person in the right place at the right moment. And I had very good co-workers that worked very hard to help me in building up the project. And we won it. And it was incredible because we hired a lot of people through the project, really a lot of people. Sorry?
Are you looking forward in collaborating with different universities or students?
No, I mean, I give you the same
Don't
answer.
worry, I will let him to have your name, but pass the exam with good notes, okay?
No, but the answer I always give is, if someone really want to work, I'm happy to work with him. But he has to work hard. That's the only thing. I mean, because it takes time to learn these things. No, but it's. I look forward to collaborations. It's such a broad area. I go from metal components for industry, for manufacturing. We do simulation of. Really opened my mind. Now we do simulation of pumps, hydraulic pumps, a very complex subject, of valves. We do simulations of bioprinting cells. So we have 3D printing in biological labs. We do all the support to surgery. We have co-workers which go to the surgery rooms. So it's really, we go to concrete, all the recycling material, sustainability is a very open area for 3D printing because ideally you only use the right material in the right place. So you can really open your application to sustainability. So it's mathematics. These are really mathematical aspects. So there are so many things to do. I'm open. We are open.
Thank you, Professor. My question is, as you have mentioned, that when you have 3D material, sometimes you may have error. So it could be like costly and time consuming. Is there a way or a process that we put in place so that we can minimize that error, so that we can produce the material?
Are you talking about this?
Yeah.
So you're saying when it moves?
Yeah. So that we can minimize the error. We can produce the material with a minimal error. Is there certain things that we put in place so that we can have the material but with a minimal error?
Again, it's... that's similar to the previous question. So let me say another thing. It's always a game in some sense. You can do everything you want as long as you are able and you want to pay for it. So in terms of money or in terms of time, in terms of effort. So you can do anything you want, but you want to be also an engineer. So you always have to decide. You can do beautiful mathematical theory, beautiful numerics, beautiful production, beautiful everything. But it's always a matter of how much time you want to spend and where you want to get it. So you can do everything you want in terms of modeling, simulations, or errors, or controlling the things. But then you need to balance your needs. So conceptually, you can do all the simulations you want in order to reduce the errors to zero or a very, very small number. But maybe it takes you 2 years to get the answer. Are you willing to wait for 2 years, or you want to do in 10 minutes and produce it? Because maybe you think that your model is perfect, and then you realize, I was showing you, and then you realize that you made a very stupid mistake. And once you see something and say, I was stupid, and then you understand it. But if you don't see it, you don't understand. So it's always a balance. So you want to be an engineer. So engineers, I think, should be effective. It doesn't matter what you do. Theory, numerics, production, you want to be effective. And the best way is to balance things. So you do some good modeling, some good numerics, some good production, you know the material, you put everything, good design, you put everything together. And then you don't minimize the error in terms of production, but maybe you minimize the error in time, that you waste. So models can do anything. It's very easy to build models. The problem is to make them physically valuable and to solve them.
Thank you. Actually, as a concern, maybe we are discussing a very complex subjects, 3D printing. So my interest is in weapon industry. For example, there are a lot of weapons that, for example, if any country attacking or another country by rocket launcher, and they having their detection system. So can we make any relationship in this rocket launcher? Maybe it change this path to so that the detector cannot detect this rocket. Can we make something in this industry, or is there anything used for weapon industry? I want to interested actually. Thank you.
You say oil industry.
Weapon industry.
This is an application in oil industry. It's from Italia. This is a very simple component, conceptually. So when you have oil pipes, they go with a very high pressure, but then they need to distribute it. So you need to drop the pressure. And they use these systems, which are basically holes where you dissipate energies. And the way they do it, so is a tube where they have 3 components inside, and so it's very simple components, but the mounting of the components is quite complex because they have these internal channels where they dissipate the energy. And you can very easily produce these internal channels with 3D printing. So this is an example from oil industry where you easily produce this object. And we were competing in terms of price. We were able to match the price of the industrial component. But it's about like 2,000 euro. Because there, for the industrial components, it was very cheap to produce the component, but it was very expensive to mount it. So the human labor. Here is more expensive to produce it, but there is no human labor. You get the final component. So it's also more reliable in some sense.
Okay, I organized last week a conference, and a medical doctor, expert in reconstruction of mandibula, was asking us a design for a patient-oriented prosthesis made of titanium. I think that we can ask you to work in this, right? It's a pity he could not come because today
this is not titanium, but this is patient specific. I mean, everything is patient specific because it starts from CT images, but this is a patient specific. I mean, you don't see it well, but it's a patient specific device because this is a part of the skull. It's the skull bone, and you can see here in black is a region where there is a nerve, and when you implant your hearing device, you don't want to touch this channel. So what do? We 3D printed the skull. We 3D printed the ear, and then we 3D printed a third component you don't see here, which is basically it's it's a small component that goes behind the ear, which just localize where the surgeon has to put the device. So you can do this.
Okay, so we
easily.
will talk about that.
We don't have a titanium machine. As I told you, I want to buy more machines, but
Is the biocompatibility of the materials that you use dependent upon the conditions in the printing, temperature, pressure? So for some kind of materials you can't overcome a given pressure level or things like that?
biocompatibility, I would say, does not depend on the pressure during printing. So, so it's more if the material is biocompatible or not. Or, you know, or if you can sterilize the material and if the material can stand the, you know, the sterilization process. So, for example, when in the last picture, let's see if it goes directly. Okay, here, you know, we do. So this is an hydrogel. So it's a very soft material, which clearly cannot go any sterilization process. So we do this 3D printing in an environment which is already working for cells. So it's a protected environment where you can also do the 3D printing of cells. In other situations, like if you print titanium, you do the 3D printing and then you go through the sterilization process. So it really depends on the material. So again, depends on the material, the process is many, but conceptually the material is, you know, can be plastic, so it depends on the specific material. So we did also, for example, 3D printing of stents for the respiratory system. And for those materials we were able to sterilize. Then there are different sterilization procedures. So it really depends. But these are very common issue.
Okay, so I think that we can now proceed. You want last question? Always at the last moment.
So that's the most difficult question, I guess.
No, it's just a small curiosity about the timeline you showed us. I mean, what was the evolution in terms of both costs and time of printing, and I guess for the next future? I mean, the cost of machines and printed object and the time of printing, how is evolving in these years? Thanks.
This is a difficult question in the sense that, so you're not talking about the investments of the machines, but you're talking about the time that it requires to produce components, basically. So 3D printing, it's a slow, today, it's a slow production technology. So it's not like stamping, you know, it's not, so it takes time, for sure. So it's not competing with the fast industrial productions rates on one end. On the other end, things are changing. So if I show you, let's see if I have a picture. I don't know if the machine is here. Yes, this machine, this is the HP machine. It prints nylon. This is not the most industrial machine that HP is producing, but there is the industrial, this is already industrial, but there is a newer, faster machine. With this machine, you can produce, we did some computations for a company. Where is my mouse? Let me show you. You can produce this set of components. These are for a peristaltic pump. You can produce with that machine 60,000 of these components in 1 year. So the production rate is not fast, but the numbers, the production, the quantity is increasing. So the technology, I really think that in the next 5 to 10 years, 3D printing will become a reality. You know, it took quite some time. It's still not an industrial reality, except in some industries. But I think that in the next 5, 10 years, it will really become a reality. And today, if there is a company asking for you to do like 1,000 components, up to 1 million components per year, you can do it. It's not easy because you need 10 machines, and each machine costs 500,000 euro. So it's like a 5 million investment all in terms of machines. But you know, when you want to do industrial production, you need to pay money. So it's getting there. The concept with people have difficulties in understanding are two, I think. One is that the material is expensive, 10 times. So you need to produce an object which is not identical to the one you already produce with the standard technology. So if you want to produce this, I can do it. It will cost 10 times. No one is going to pay 10 times if you produce it for 10 times less. So I need to change the geometry. I need to do more ergonomics or, you know, much better feeling, whatever. But you need to give it like a value which gives the different price. So material is expensive, but you have freedom in terms of geometry. And the other thing which is really incredible is flexibility of the production. I don't have, well, I can show you again this picture, which is not very, I have other pictures, but if you see this picture here, this is a very interesting picture because you have, in one production, you have components with many different geometries. If you have a milling machines or, you know, other production, industrial production technology, you don't do this. So if you have a production factory, if you start produce like 1 million of components, you will lose a huge amount of money if you say after like 500,000 components, let me produce like 100,000 components of a different object, or let's change a little bit the geometry. It's impossible. Once you do the investment, you need to produce the same, you know, the specific amount of components. Here, who cares? Conceptually, you can produce like 1,000 components, and then you produce 2 components different, then you produce like 50,000 components, then there is an urgent, you know, need for you produce. So it's a very flexible production. So you can, it's not exactly like this, but now I'm putting simple. But conceptually, you are extremely flexible in terms of productions. So with the same machine, you can produce without doing anything different, just sending different files, objects which are very different. If you have your milling machines, you know, these machines, so we have it. It was very, very interesting. It's not a cheap machine. It's not cheap to run it. You know, this 5-axis milling machine, besides it's huge, besides it's dirty, to run this machine is much more complex than to run the, you know, to do this work, this excavation was much more difficult to produce the component. So standard technologies, maybe they're faster sometimes, but you know, they can give you problems.
Okay, so I think that now I can ask our friend, Professor Russo Spena, who is also the president of the Accademia d'Abruzzo, to present our medal and our parchment to Professor Auricchio. This is a prize which is delivered by the MEMOX Center to outstanding personalities in mechanical sciences and applied engineering. And
Thank you, Professor Dell'Isola. I prefer to speak in Italian. Dunque, perché sono rimasto veramente colpito dalla relazione del professore Auricchio, che viene da una scuola prestigiosa, la stessa scuola, l'Università di Napoli, dalla quale provengo io, e abbiamo avuto dei maestri in comune, il professore Giangreco e il professore Sparacio. Mi ha dato l'opportunità il professore Auricchio di ricordare una relazione che aiutai a preparare il professore Sparacio a proposito della funzione dell'ingegnere alla fine del XX secolo. Siamo negli anni 1970. Si domandava il professore Sparacio, che doveva fare questa relazione all'Ordine Nazionale degli Ingegneri, quale fosse la strada da seguire. Gli capitò tra le mani un testo di un fisico, storico diciamo della fisica, con trascorsi da fisico, che aveva fatto uno studio veramente interessante. Si era domandato quanto tempo occorre perché la conoscenza, lo sviluppo tecnologico si realizzi in una società. Ebbe un'idea, secondo me, geniale, perché prese in considerazione tutti quei parametri che sono facilmente misurabili. Per esempio, la velocità delle automobili, quanto tempo occorre per passare da una velocità massima di 100 km all'ora, forse probabilmente nell'inizio del secolo 80-50 km all'ora. Ricordate che Rossini, il grande compositore italiano, fu colpito da un viaggio in treno, la velocità del treno, circa 50 km all'ora, lo portò fuori di testa e Rossini è morto esaurito, perse tutti i capelli, perse i denti. Fu molto ben accudito dalla moglie. Vabbè, ora non mi dilungo, se no prendo un'altra direzione. Quanto tempo è occorso quindi per passare dai 50 km all'ora dell'inizio del secolo, diciamo, ai 300 km all'ora della Ferrari, con la quale si può muovere attualmente. Oppure, quanti numeri di telefono e quindi quanti abbonati telefonici ci sono stati dall'inizio del secolo alla fine del secolo. Bene, si accorse da questo studio, e altri parametri ancora, si accorse da questi studi che il tempo di crescita dello sviluppo tecnologico, il passaggio da un numero a quello raddoppiato, richiedeva 15 anni. Era straordinariamente regolare la crescita. E io ero convinto, quando mi sono laureato, che questa crescita mi sembrava anche ragionevole, sufficientemente pacata, fosse possibile ad ogni giovane laureato di avere perlomeno 15 anni di tempo prima di dover rincorrere le nuove tecnologie, i nuovi metodi di calcolo e così via. Ora faccio soltanto una brevissima considerazione sulla bellissima relazione del professore Auricchio, densa di riflessioni, perché produce non soltanto riflessioni tecniche, ma produce anche delle riflessioni epistemologiche, filosofiche molto profonde. Dove va il mondo? Bene, 2300-2500 anni fa, il fondatore della matematica, dell'ingegneria, della fisica, come lo chiamava Galileo, il divino Archimede, studiava per la prima volta i problemi di meccanica. E nello studio dei problemi di meccanica, il nostro divino Archimede, il grande siracusano, il più grande matematico della storia, così è noto, studiava i problemi delle macchine e quindi delle strutture, mettendo alla base dei suoi ragionamenti i postulati di Euclide. Per lui, quelle che noi chiamiamo trave, o meglio ancora chiamiamo solido monodimensionale, oppure chi si occupa di meccanica dei fluidi chiama corrente fluida, tubo di flusso, per lui era semplicemente una linea geometrica. e a questa linea geometrica non dava assolutamente nessuna proprietà, se non quella di essere appunto una retta, quindi di non potersi piegare, di passare da un punto all'altro con una minima distanza, e a questa retta, che aveva solo questa funzione di sostenere dei pesi, ricavava poi una serie di teoremi di cui noi tuttora, con un modo completamente diverso, noi sviluppiamo. Guardate che disse qualcosa ancora di più. Vedete, parlare di Euclide significa prendere la materia, prendere un oggetto, privarlo della materia e studiare intrinsecamente le proprietà di quell'oggetto in base alla sua forma. Arriva alla sublimazione Archimede di questo concetto, perché immagina di trovare il baricentro dei corpi. Per trovare il baricentro dei corpi non è necessario che i corpi abbiano materia, siano fatti di materia. Quando a lezione o agli esami o voi stessi eseguite i vostri calcoli, voi non è che disegnate precisamente il cerchio, voi disegnate uno schema e su quello schema fissate un baricentro, perché sapete che una volta realizzato quel sistema, qualunque sia la materia con la quale voi lo realizzate, il baricentro si trova non al centro della materia, ma si trova al centro dell'ombra della materia, cioè di qualche cosa che non è materia. Ora, si potrebbe naturalmente, potrei portare la questione molto più avanti, perché la meccanica di Archimede è avanzatissima, contrariamente a quanto si può ritenere. Nella meccanica di Archimede è riportata la meccanica di Aristotele. Aristotele è considerato un pensatore filosofo molto astratto, pensava alla realtà fatta di potenza e di atto, parole che sono rimaste nella nostra fisica, però interpretate in modo balordo. Lo ridicolizziamo ancora e spesso si sente nelle aule universitarie, dice, questa è l'ipotesi di Aristotele. Aristotele è l'inventore o è lo scopritore del principio dei lavori virtuali. E il principio dei lavori virtuali è stato applicato da Archimede. E con un salto di 2000 anni, provate ad andare a Newton e vi accorgerete che quel principio dei lavori virtuali Newton non l'ha capito e non ne ha mai fatto uso. Per vedere il principio dei lavori virtuali dovete aspettare Leibniz, anche il nostro Galileo ha intuito per la statica. Il principio dei lavori virtuali si applica anche nella dinamica, ma per avere il nostro modello dovete arrivare alla Lagrange, che il professore dell'Isola vi ha richiamato poco fa. Dunque, quando uno studente entra nelle aule universitarie impara Archimede, naturalmente, perché lo si impara, poi si impara Newton, sembra quasi di aver finito, ma invece poi gli ributtano addosso le equazioni di Maxwell, sembra di aver finito, e poi si ritorna con la meccanica razionale, si ritorna un'altra volta a Lagrange, che con la sua lagrangiana costruisce mondi. Allora dice, ma tutto questo con la relazione del professore Auricchio che c'entra? Ma non è proprio quello che ha fatto vedere, non è l'ultimo passo al quale l'ingegneria sta arrivando? L'ingegnere, guardate, non progetta più la struttura in quanto tale, progetta il materiale con il quale realizzare quella struttura. È fondamentale questo, perché lui riesce, e bisogna ringraziarlo, perché è il fronte di questa nostra disciplina, meravigliosa disciplina, alla quale non dobbiamo arrenderci, perché le questioni che ha sottoposto oggi il professore Auricchio, fra 15 anni, se si mantiene il ritmo purtroppo è molto più breve, di De Solla, sono superati. Anche il professore Auricchio dovrà correre. Non so se avete letto, e chiudo, non so se avete letto mai Alice nel Paese delle Meraviglie. Io consiglio a tutti questa lettura, che è particolarmente istruttiva. Alice domanda alla regina come mai stanno correndo, però si trovano sempre allo stesso punto. E dice, ma questo è un paese molto strano, sta nel Paese delle Meraviglie, questo è un paese molto strano, corriamo, e io sto sempre ferma qua. Dice, perché da voi che succede? Domanda la regina. E la regina risponde alla regina, ma il vostro è un mondo veramente strano. Se voi correndo vi spostate da un posto all'altro, è un mondo veramente strano. Noi se vogliamo, attenzione alle parole, se vogliamo rimanere qui dobbiamo correre. Se vogliamo andare lì dobbiamo correre almeno il doppio. Che significa? Se vogliamo rimanere al livello individuato dal professore Auricchio, dobbiamo correre, non camminare. Se vogliamo andare avanti al professore Auricchio, dobbiamo correre almeno il doppio. Allora, siccome sono esempi importanti questi di ricercatori che portano avanti uno stadio di ricerca estremamente avanzato, che non dimentica il passato, perché noi siamo legati ancora ad Aristotele, siamo legati alle forme di Aristotele, che non sono astratte. Nicole Doresme, sulla base delle forme aristoteliche, le interpreta come fenomeno misurabile e inventa la nozione di funzione. Le forme di Oresme sono utilizzate da Galilei per lo studio della caduta dei gradi e guardate, per la dimostrazione del principio di inerzia. Lui dimostra che un corpo non dimostra matematicamente, una cosa che non si potrà mai verificare, che un corpo mandato con velocità iniziale assegnata su un piano orizzontale si muove con velocità costante. Lui verifica questo risultato. Non abbiamo tempo per farvelo vedere, ma è delizioso. Quindi, siccome il professore Auricchio queste cose non solo le sa, ma le fa, è un esempio molto importante per la nostra scuola, anche per i vecchi, perché anche io continuo a correre, no? per quello che mi è consentito, con la velocità che ho. Con l'età vi accorgerete anche voi, ci vuole tempo, con l'età vi accorgerete anche voi che c'è una cosa straordinaria. Più si invecchia, più la capacità costruttiva si riduce, più aumenta l'atteggiamento critico. E la capacità di produrre si riduce non perché uno è meno capace di produrre, ma perché l'atteggiamento critico è così violento che appena preparate qualche cosa lo criticate e cancellate tutto e quindi non si procede più. È necessario per poter... no, però è necessario, se vogliamo procedere, è necessario essere giovani. Quindi bisogna fare molti figli. Vabbè, ora rischio di fare un ragionamento che non è fuori posto. Allora, alla luce di quello che ho sinteticamente detto, avrei voluto dire molto di più, ma non voglio abusare della vostra pazienza, devo ringraziare innanzitutto il professore dell'Isola. Perché ringraziare i professori dell'Isola? Perché pensare a un premio basato su queste ricerche internazionali di meccanica applicata, quale organizzazione che ha pensato lui, che ha realizzato lui, e aprire all'Aquila, una città che è stata tormentata da una catastrofe terribile, della quale ancora non ci riprendiamo completamente, è un merito, quello del professore dell'Isola, è un merito alla quale la città dell'Aquila del quale la città dell'Aquila deve avere un ricordo eterno. Io lo ringrazio come cittadino aquilano, ma lo ringrazio come presidente dell'Accademia delle Scienze d'Abruzzo, che è nuova, giovane, ma annovera tra i suoi soci personaggi di rilievo internazionale. E tra l'altro ci sta il professore dell'Isola, è uno dei nostri rappresentanti, abbiamo rappresentanti dell'Accademia delle Scienze d'Europa, abbiamo rappresentanti delle accademie nazionali, delle importanti accademie nazionali. Però nel nostro piccolo, nella nostra gioventù, cerchiamo di diffondere questa cultura e questa meravigliosa storia della città dell'Aquila. Allora io veramente ringrazio il professore Auricchio, spero di non averlo annoiato con le mie considerazioni, lo ringrazio molto, gli do questo diploma. Ma gli do qualcosa di più, c'è una medaglia che è veramente... Si è perso il...
questo lo mettiamo dopo.
Una medaglia che è veramente avrà modo lui stesso di apprezzare la fattura. Caro Ferdinando, veramente grazie a te.
Grazie moltissimo,
I will translate at the beginning of the next lecture this, because it is very interesting. You know, we people from Napoli have a fixation with ancient Greeks. So also Professor Russo Spena said something about that. Don't worry, I will tell you everything in detail. Grazie ancora.
Sì. Well, it's hard to say more, but I wish to thank Professor Russo Spena because he brought, I mean, it's hard to transmit the meaning of some of the things he said, because he went back to the to Professor Giangreco and Professor Renato Sparacio, who have been my major advisor when I was a student, and I should say that you find a lot of I hope a lot of their inputs in my presentation, which is in some sense incredible, but they were two very, very important professors. And at the same time, I think that they were exceptional because they really liked life on one end, but they really liked engineers. And when I say engineers, I go back to the answer I gave before, which means that they both were extremely practical, I think. So it doesn't matter which theory you do, how much mathematics you do, but at the end of the story, you want to do advances. You want to transfer something. And I think that both Elio Giangreco and Renato Sparacio were extremely practical, because they were also very theoretical, but at the same time very able to do some steps forward. And going back to I really appreciate when people talk about the old history, engineering history, because I think that also, in the presentation, I can show you integrals, phase field theory, very complex mathematics, which is extremely powerful. But especially working with mathematics, you realize that sometimes models and concepts are also very simple. So they're very complex in certain aspects, but at the same time also very, very simple. So it's good to go back to the old roots and to find in the complexity of the future, of the engineering of the future, also the simplicity of some concepts, really. So you need to be driven, I think, by the beauty of the complexity, but also by the beauty of the simplicity, which is fundamental to make good results. So thank you very much for the invitation, for the medal, and thanks.
Okay, thanks to everybody for being here, and for the students, we will meet tomorrow, okay? Thanks a lot.